Now we continue discussing how to adjust model parameters to reduce the loss. We have established that we will start from the output end of the network, that is to adjust the output to reduce the loss, to the beginning part, to the input end of the network. Along all the way, we'll pass information of how to adjust the output so that the loss is reduced over all the parameters in the model. We have discussed how to perform this kind of computation when we are discussing one computational step where there is one output. For example, we have discussed if we want to, we will need to change the output B, which is the result of computing the input of H0 and H1 with the model parameters U0 and U1, and how to change U and H so that B can change, so that Y can change, so that the loss will reduce. And in the second part, we'll technically, though essentially the same, but technically extend this line of thought so that it applies to computational steps where there are multiple outputs as well as multiple inputs. To be specific, we will discuss how to calculate the gradient with a gradient of the output using the gradient of the multiple output and calculate that the derivatives with respect to the parameter matrix. As an example, we will move to this step. Say we have calculated how the change in H0 and H1 affects the final loss or the Y. They are the same kind of information, and it is applies the same kind of technique to calculate how the changes in A0 and A1, because A0 and A1 are mapped one by one to H0 and H1. So if we know the influence of H0 and H1, we can use the same kind of calculation as we have discussed in the previous video to calculate the influence of A0 and A1. Now we have A0 and A1, and we have the input of X0 and X1. Now we want to calculate how the change in this parameter matrix will affect the final output, say Y. As a concrete example, let us say if we change A0 by 1 unit, Y will change by -1 unit. If we change A1 by 1 unit, Y will change by 0.5 unit. And in this case, let us see how the value of the W parameters affect the output of A and therefore affect the change in Y. So recall that for the sake of making animation, I have put this. I have used this superscript to represent the association with X. So W superscript 0 will be associated with X0. W superscript 0, 1 will be associated with X0 as well. And the subscript will be associated with 0, 1, 0, 1 with the output. So W superscript 0, subscript 0 will be associated with X0 as the input and will be contributing to the value of A0. And correspondingly, the other W parameters will be combined, be associated with the corresponding X input and contributing the corresponding A output. If we write the relationship, we collect all the relationship in this way. If we collect the influence of W0, we will have, let's look at this computation here. X0 combining W0 contributing to A1. So how W0 affects Y is determined by how A will affect Y, which is known at this step. And because the computation goes this way, A0 is X0 times W00 plus X1 times W10. So W00 contributes to A0 through X0. So this will be multiplied by X0. We can do similarly considering this part of the parameter. So W superscript 0 subscript superscript 1 and subscript 0 is also using the influence of A0 to Y, and then is multiplied by the value of X1. So it is not difficult to imagine, because this part where the subscript is 1 will contribute to another output A1, and so in this part we will have the influence of A1 to Y, and the multiplication is by X0 and X1. So we can see that in the row of this derivative matrix, in the row there is a factor of X. So we have this to contribute to the row of the derivative matrix, and the columns is determined by the known influence of the output to the output of this step of computation to the final output of the network. But actually, in the practical computation, this should be the influence to the loss. But as an example, as long as we can summarize the influence to a single value, it is fine. If we write out this format in a matrix form, that would be the X vector transpose, that means X0, X1. Using matrix multiplication by the derivative, the gradient of the output of this step of computation. That is, let's say, A. This format is general. It's not limited to the case where we have 2 inputs. We can have more inputs. And we can have more output. in which it will collect the contribution of all paths and give us the gradient of the appropriately sized parameter matrix. So the multiplication gives us this, how each of the W element affects the output of the network. And this is also applying to the case where we are calculating the derivative with respect to multiple training samples. If we have multiple training samples, well, in this case, I'd better to adjust the final interested quantity from the output of each samples to the final output of loss function. Let me write it in this way. Okay, please excuse me. Now we have multiple training samples. The X matrix will be X0, X some value. And we have another sample, X0 to X, the number of attributes. And if you recall that, we often use this to represent the index of the samples. We take transpose, it will become this way. And the output becomes this way. So let me reorganize that. So this dimension goes to the go over the number of samples. And in this dimension, it is the number of input variables. And this dimension is the number of output variables. So we take the multiplication in this way. Therefore, that will give us the gradient of W matrix. And let's take a very specific example. This is the ith row and the jth column. The Wij will contribute to, if we recall the arrangement of this computation, if we go this way, the Wj will contribute to the jth output, and by collecting weighting and summing with a sum of the I shouldn't be here. I of all samples. So the derivative of Wij will be the sum over training examples, let's see L. XIL. The L samples I attribute is combining with Wij and contributing to the G's output. So this is using another way to explain the matrix multiplication. So to summarize, when we're calculating the derivative of the final output, I should have used loss. It's better but this example is simple. I should have used the total loss when we consider multiple input samples. When we considering the influence of a matrix multiplication, the parameters in the matrix multiplication, we will use the influence of this output and combine that with the input of the multiplication and get the parameter gradient